Okay, so doesn't it look like we have some less light today?
Yeah, these lights.
Okay, so what we're going to see. Okay, so before we even start today, when we say that we pick a random function, what does it mean that we pick a random function, right? So last time, if you notice, we were trying to say that, okay, let's choose a function f1, f2, f, say q, with certain properties, right? And these functions were created randomly. And what was the meaning of that they were created randomly, right? We were basically picking some subset of elements, right, randomly. This is basically what it was. So basically, you can think of these functions from a universe to 0, 1, right? Right, which basically picks a subset from here, right? Now, what I would like to tell you that before even go in any of these things, suppose we have n random variables, x1, x2, xn random, like completely general stuff. What it means to have when we say suppose this is an over 0, 1, like very simple set of random variables. Each xi takes value 0, 1, okay, with uniform probability, okay. Okay. Now, but if xi is a random variable, it takes value 0 and 1, but sometimes if you notice, say, look at example of max cut, right? Look at example of a max cut, right? Look at example of max cut. Now, what do we do in the max cut, right? So I can think of max cut a partition of a vertex at Vg based on, I can think of this partition P as nothing but, well, this partition is defined with respect to help of some function of x1, x2, xn. And what is this? Well, those guys which takes, so and what is this xi? Now I will have xi for every vertex. So suppose vertex set is 1 to n. So now what I have assigned to every vertex of a random variable which takes a value 0 and 1. Now, so these are my general situation which you will see quite often. And now when you say, okay, look, now I'm going to define a partition of vertex set based on this random variable x1 to xn. What is the meaning of this? So what I'm going to do, okay, if these guys take all the guys, look, if x1 takes, so I'm going to define a partition by just looking at these guys and taking a set which all values, whichever takes 1, I take it in one side and 0 in the other side. So that clearly defines a partition. So a partition is also a random variable which depends on x1 to xn, right? Based on the what xi's take, I can define a partition. But now what does it define? This world defines, or this defines, now this is also a random variable, okay? Or think of this as a random partition, okay? Or think of, if you do not want to think of this as n random variables, you could also view them as random partition itself, okay? So forget about this. Now you can think of, if you do not want to, this is one way of thinking. So it's just a function from 0 to 1, right? I can think of each partition as a function from 0 to 1, and suppose this is a random function from Vz to 0 to 1. So that gives me a random partition. But what is the domain of such? Well, like, what is the domain?
Domain of what?
Like, what all this can generate?
Yeah, some 0-1 sequence of strings.
All partitions. Yeah, it can generate all partitions. Right?
Partitions of the
Vertex. So in other words, this is nothing but, basically I can view this, think of this as a matrix. Okay, let's think of this as a matrix. Okay, what is this matrix? Matrix has a rows and columns. Basically, columns corresponds to vertex v1 to v n, and what is this rho corresponds to? Some functions, right? How many such functions are there? Q is like 2 power n, right? So selecting a random function from Vg to 0 1 is same as selecting a row from this matrix uniformly at random, right? Selecting a random function is same as selecting some rows from this matrix uniformly at random. Okay. Now when you say for example, I will tell you that okay, my functions are pairwise independence. What is the meaning of that my functions are pairwise independent? Basically what it says, if you notice what it says, okay, I have a family of functions FQ, basically your rows, right? For rows, what basically it says that for any two things, okay, if I restrict myself to my image of two vertices, two guys, say Vi, Bj, so that restricts myself to some two columns, okay. When I restrict myself to this two column, what are possible outcomes are 0 1 or 1 0. What are my possible outcomes are 0 1, 1 0.
Oh yeah, that 3 4 possibilities.
Right. So now if I put myself a window to be just two guys, restrict myself a window to two guys, the probability that I will get one of these vectors is proportional, is uniform over this space, right. So if I restrict myself to two guys, right, and look at just this world, then I will get each of these entries with probability equal to 1 over the size of this. So it is uniform over this world. So when you say that it is 3 wise independent, what it basically means that if you look at 3 guys and look at those three columns and look at the vectors which you can generate, right, look at the objects which you can generate, so it is uniform over this particular set. That is all that it means. Okay. Now the question arises, of course, if I take each functions f1 to fn, right, if I take functions f1 to fq, where q is 2 power n, all possible functions, you can clearly prove that any wise functions is enough. Now imagine yourself, I am interested, I said look, I am not interested in anything, but I am interested in a matrix, like not say this matrix is M full, okay, M small, whatever that M small means, which has the following property. It is still a functions from V1 to Vn over 0 1. Let us call these functions G1, G2, Gq prime, and even now when I look at any two columns, it is these objects are uniform over this space, okay. Do you get the point, right? But now all I am asking you that no, this q prime cannot be large, q prime should be small, okay. So I am looking for set of functions, okay, when I look at the window of two columns, right, it still behaves exactly the same way this set of functions were behaving before, right. I cannot guarantee when you say 3, I cannot guarantee that if you take 3 guys then and you generate all 0, all 3 length 0 1 3, then I cannot guarantee you. But if you just take all this thing, you take any two column and look at the projections of those guys, it still happens with uniform probability, okay. This is what it means to say pairwise independent. So if all I want is that set of functions with the following property, that if I take any two columns and I look at these guys, okay, look at these guys, then it is uniform over this space. That is all that it means. Now people have defined, okay, why 0 1, people might need a larger domain, okay. So you define it over some b, But now how many rows will be there? It will not be 2 power n, but it will be b power n, right? But now what it will be? It will be some, it should be uniform over b power square, like all tuple b cross b, it should be uniform over this. And this is about 2-wise independence, 3-wise independence, 4-wise independence. And the great thing is there are functions which will achieve this, right, of size n to the power square, some order n square for any b. Maybe there is a b in the term in the beginning, it might have, but I don't think we have. No, yeah, it doesn't matter. If b is fixed, then it doesn't matter. Let me tell you a hint. Where do you get this function? Okay. What are the uniform matroids? U and K. I have taught this several times. Universe is 1 to n, right? And what is my family? All S subset of U. This is what it is, right? Right? This is what it is. What is the representation of this? What is the representation? So what is it? Tell me precisely. No, I never said that. I want a representation means I give a bijection from universe to columns such that if something is linearly independent here, if and only if it is in my family. So it was 1. Basically, it is you choose some n distinct numbers from a field, sum doesn't matter. It's basically x1 0, x1 1, x1 k minus 1, x2 0, x2 1. What is the dimension of this matrix? It is k cross n, right? It is k cross n, right? It is k cross n. Now, it is a k cross n matrix. But what is the property of this? Since it is a k cross n matrix, why you people can't come on time? Really, I mean, then don't come, it's much better. It breaks rhythm of people. Right? So, now what is the property of this? What is the property? If you take any k plus 1 columns, are they linearly independent? Columns. Why?
It's uniform matroid with k uniform matroid. So basically all the independent sets in the uniform matroid are of k sets. So any k.
That's not the reason, Rani. Please look at what it is written. I ask very simple. Why any k plus 1 columns?
Because
it is, look, whether it is a representation or not, we don't know, right? But the very fact that any k plus 1 columns is linearly dependent just follows from the fact that this guy has only k rows. So the dimension of this matrix is k, at most k. So any k plus 1 for sure. And now since it's a van der Waals matrix, you can show that any at most k size object is linearly independent, because the determinant of corresponding submatrix will be non-zero. That requires proof. But this is also a construction. This is also a construction. Right? this also tells you the what kind of constructions one should be looking at. Okay, so basically what happens is that what you look at it is that how do you construct such functions. So if you remember for 2, all you create is that you take some field f, okay, and basically you take ax plus b for all a comma b in f star times f star, where it is like non-zero interval. So basically you take all those functions. What is the functions? Function has an universe, right? That's okay. But what you do is that you basically you have a family of function f a x plus b, which basically what it means is that f a x plus b of something is nothing but a times something plus b. This is what it means, right? For every a comma b, you do this, and you can show that this has all the basic properties. But if you notice, it is a 2 uniform family. Okay, but domain is how you should take care of domain, range. There are some small tricks, but this is what it is. So if you are looking for a 3-wise, what is this? You go over a comma b comma c in triple, and basically what you will do, ax square bx plus c. Okay, so you will have how many choices? Triples are there, n cube, right? And if you are looking for 4-wise, you will take ax cube bx square cx plus d or something. Okay, and why does the proof will work? If you just work, you will get exactly this. So in the heart of the proof is basically Vandermeer matrix, which is sitting there, which basically captures everything which is k-wise independent, and it says nothing about k plus 1 or something more. This is what is hidden in the proof. Okay, but I hope you should people have seen these constructions anyway already by now, so I am not going into it. Haven't you people seen the construction of 2-wise independent random variable? But that is not what I was planning to tell you. How do I look at 2-wise random variable? Okay. Basically, the way to view them, okay, it was just to give you some idea of how these things are. If you look at the proof, then you will see that this matrix will come to show why any k columns are independent. What did I say to you? That if I look at any k guys, they are going to be uniform, right? They're uniform. And if you look at the proof, basically this is what it will make you uniform. This is the kind of idea which will make you uniform, because look at this, right? What it will be, some ax square plus bx plus c, right? So it will be some 3, right? It will be some 3 things which is going across linearly, and you will have to show that those kind of things do not vanish properly. I hope that you people have seen this proof.
I don't see the connection between
The connection between what?
I don't know where are we going. So
We are not going anywhere. All I am trying to tell you is that there are objects. Look at this objects. This is one object where any k things is linearly independent, but any k plus 1 things are not independent. What most of this construction of independent random variables does is basically essentially tries in its proof something of this nature to prove its correctness, to prove. So independence in probability space is mapped as independence in some matrix. Okay, so if you read the proof exactly, for example, you just take this affine function ax plus b and try to prove that what does it mean. I have not yet defined what it means to be. Or did I tell you that what I mean by 2-wise independence? When I look at this guy, it's uniform over this. How I am going to prove this? Now I have so many functions, right? I have so many functions. Okay, over some universe. It doesn't matter what universe it is, right? So what it means, so like it is going to give you some numbers as you vary your universe. So suppose I have a universe 1 to n, okay. So 1 to n, right. If I compute this function a and b here, I am going to get some vectors here, right. I can take to some mod 2 arithmetic to make it 0 1, for example, right. If I had to do, then I will do some mod arithmetic to make it Boolean, if, right, but for now don't care. So you have these functions, and what you have to show? You have to show that if I look at any two guys, right, any two guys, and whatever objects I wanted to get in my domain here, then this is same. Now just try to visualize how the proof will go.
I think I recall.
What? No, but I am not interested in proof. That is not what my motivation is. So please, okay. But this is not what I want to communicate. That's part of the different course. So this is how you construct, and when you try to prove this, you will see this matrix coming in. Okay, but that's not what I want to convey in this lecture. Okay, otherwise I will derail. Okay, so what I want to convey is that suppose I have a universe and I have a domain. Okay. So what I am going to have is a universe and domain B. Universe is going to be 1 to 1. Okay. Now let's take a random function f from u to b. So what is the property of this random function? For all a in u, f of a is 1 over b. It is assigned one integer from 1 to b with probability 1 over b. This is exactly what it means to have a random function. Okay, fine. Okay, f of a is sorry I in b with probability 1 over b. Or for all a in u, I in b, f of a equal to I with probability 1 over b. How do you construct such functions? You take this, you assign one of the integer from 1 to b with probability 1 over b. This is what it is. Okay. So now if in some algorithm, so this is my random function. Okay. Now what happens is that if in some proof all I am using, so this is, I can think of all I am using is certain kind of dependence, some limited independence. So what is this? What is this random function? It is a function, right? I mean, it's basically a function from universe to 1 to b, right? And when you consider this, it's basically like choosing from all functions from universe to b, one with probability 1 over b. This is what it means, that I am going to choose one of the functions from this world is same as choosing a function in this way. I choose one function from this whole world with 1 over the cardinality of all the function space is same as choosing one function from here with this, like with this random process. Okay. Now what I said, whenever you have a limited independence, by what I mean a limited independence, so suppose you have an algorithm which uses some, which is a randomized algorithm, uses some n random variables, okay, but with a limited dependence. I mean, all in the proof analysis, all you have used is that, oh, probability that xi equal to a and xj equal to b is probability xi equal to a times probability xj equal to b, right? So if two random variables are independent, then this is, so even though you started with that, all these are like all x1 to xn are like not only pairwise, they are just independent random variables. Like you take any subset, this holds, but in the proof all you use is just this. Okay, then you don't need to, then you don't have to go over all these functions, but there are a small number of functions which behave exactly the same way. Okay. So for example, this is what I said, right? For example, what did we say? For example, let's look at the max cut example, right? You said look at a random partition, or you have an x1 to xn random variable, okay? And what you say? Okay, let's how do you do? For every vertex v, you what do you call? You toss a coin. If it comes head, you put in the set v1. Otherwise, you put in the set v2. So how many coins are you going to toss? N coins. So these xi's are random variable corresponding to your vertex set, right? And each takes head or tail with probability half, right? Because and you put them. Now suppose if I wanted to show that expected, okay, max cut has size at least m over 2. How do we prove this? How do we show this? We say, okay, fine.
Okay, now let me know.
Everybody knows this. That's not the point. So I have a random variable for every edge, which is 1 if edge is in cut, 0 otherwise, right? So if you do your computation and x is summation of xe, so expectation of x is nothing but m over 2. If you do computation, you will get exactly this, right? Because for every, if E is uv, right? So when this edge will go, if xu is 0, xv is 1, or xu is 1, xv is 0, and you can do all this computation, right? So this is m by 2, right? But let's look at the computation of expectation of xe. What did you compute? How did you compute x expectation? How did you compute probability of xe? Is exactly how I computed this. So probability of xe, I computed probability of xe is probability xe is 1 and xv is 0 and x equal to 1, or probability xu is 0 and xv is 1. Although I could have started with x1 to xn random variables which were this, but look at the computation, all I am using is that 2 of them should be independent. Okay. Now the question is, then do I really need this? So what does this mean? This proof tells us that there is a partition, there exists a partition. So from this information, what did you conclude? There exists a partition with at least m by 2 edges going across, right? This is what we concluded, right? So I came up with a partition, right? So what happens is that if whatever properties you are able to deduce about these random objects, right, with limited dependence, you will be able to say that, look, what did you say? That, look, oh, there exists a partition, right? But there exists a partition across all partitions, there is a partition. But now all I used is this. So now I will tell you, look, let's not look at let's not look at all these partitions. In polynomial time, I'll give you some functions fq or some partition, however you want to view it, that anything you can conclude by just this much. So you have your random process where everything is completely independent. So you have a random process where everything is completely independent. Okay. Now whatever you are able to conclude with 2 people being independent, just pairwise independent, then this family, there exists a function with that property. That is what it means, and this is how you use it, right? Now there is a proof to conclude, but this is how you use it. So you go back, everyone is completely independent, and you do some computation. Now look at how many things, how many independence have you used. suppose it is bounded by 2, 3, 4, 5, 100, right? Then anything which you can conclude by everything being independent, but you are using only 100 things being independent, you can conclude from this world, right? So what you did, you said that look, if all I am using is this guy's limited amount of power, then I can find you some small number of functions from here, right, which has all these properties. So from the perspective of just these two guys, they are uniform, nothing changes. All you use here is the two of the people who are independent, right? So why do you want, where did you use the fact x1 is independent, x2 is independent, xj is independent, xk is independent? No. The point is anything which you can conclude, anything you can conclude from here, there is a function which satisfies this property. This is what it means. So this is other way to utilize all these limited independent functions, right? So always, I mean, there's no magic happening here, right? Of course, there's a magic in the construction of these, but let's forget about that magic. But if that construction is given to you, how should you use it? That is what I am interested in. No, I am not interested in how to construct that, but how to use if someone has given me. So how I use it? I said fine. Suppose everybody was everything, because then that makes your maths simpler. I'm able to conclude something. Okay, is this much independence this is? If it is, then there is a function which satisfies this property. Let's just go ahead and use it and be done with it.
When you say use it, you mean you're only interested in, suppose the way you use is only in the following way. If you're interested in finding out that partition, is that the only way?
Yes. Only thing which you can conclude from this guy is what you can conclude by using pairwise, nothing more. There could be many things I could conclude from just two things here. For example, I could also say with two things, how many, some lower bound and upper bound and edges here and here, if I am able to conclude. Then there is a partition here with that property also.
I'm saying, why do I make such a family? Only because I'm interested to, you showed me probabilistically.
Right?
Yes. And in the probabilistic experiment, whatever you did was you did some, your events were all independent.
Yes.
Right?
Yes.
But now, when you see this calculation, you realize that it's only two was independent.
For my purposes.
And then you come up with this family. This family.
No, this is a universal family.
Yeah.
This is not a family which depends on your property. This is what I am trying to tell you. This is a family which only depends on two numbers, a universe and domain.
I'm saying, what is the purpose of this family? The purpose of this family is only if I'm interested in finding out that nice thing that is.
But this nice definition of nice, yes, you are completely correct. But in a different application, my nice meaning will be different, right? But I am using the same function. So what I am saying that these functions are not prepared. Look, these functions are not prepared using your utility. These functions are prepared using probability and using this 2 point that if I look at any two columns, then it is uniform. So, right, this is it. So, any algorithm or any property which you can deduce by just these two statements, you will be able to deduce it. So these functions are not property dependent, but these functions are probability dependent, or the how things correlate to each other, how things are independent to each other, right. So this is why I gave you this example of a matrix and columns and rows, right. Now it could be anything, right. So basically so for example, this is what I said, right. Look, I gave you a static function, okay. I gave you the static function. Anything you can deduce with 2 about these partitions, anything you can do this. Now I could have a different application, right, where using this I am trying to conclude something very different, right. I have the same static functions. So the functions remains the same, and you as a user, whatever you want to deduce, you say, hey, there is one function here which does this job for me, right. So I prove probabilistically because it is easy to prove for me, right. But to make it deterministic, I say one of these functions does my job, right. So for example, I will give you an order n square partitions. What I will give you? I will give you order n square partitions. One of them has this, but any other partition, any other property which you can prove with respect to 2 is also there, right. So any property which you can prove with so don't think at a property, think from the column perspective. Anything which I can prove with the fact that whenever I look at any two columns and look at my domain, right, with respect to domain, this is uniform. Like, please keep that in head. That is why I draw this matrix picture, because that is the right way of looking at it, right? If you look at property wise, then it becomes property dependent function, but we can never have a property dependent function, because then that does not mimic my random process, right? So what you are trying to do using this function is to mimic the random process, not the outcome, right? So you are trying to mimic the random process, not the outcome. Okay, so there's a very beautiful constructions of all these things, and one construction which I will use today is, I'm not going to give you the construction, but I'll show you its application. For example, I'll give you a very good example. Okay, for example, okay, I also want to conclude what is let's V1. So this is my process. What is my process? This is my process. I just told you process. X1, X2, Xn, and it has taken 0, 1 with probability half. Okay. Okay. Now, okay, let Z be a random variable which is summation of xi, I going from 1 to n. What is this? What is this random variable tells you?
That's Z.
What is this random variable means?
Number of successes in n.
Or basically
Number
number
of partitions in one partition.
of vertices in one partition. What is this? What is the expectation of Z? Huh? N by 2. So there is also a function there which will have this property, that should it have or should it not have? Look, do you see what I am asking question, right? Z is a random variable. Expectation of Z, all of you said just now, is equal to n over 2, and you are completely correct, it is n over 2. But what does this mean? It means there is a partition. It means if all xi's were all n wise random independent random variable, there is a partition where both sides are like roughly n over 2. I am asking you.
If they were all the same, then what? If x1 equals x2 equals up to xn, then everything will go on outside. Yeah.
Look at the what is the probability that xv is 1? It doesn't depend on any of them.
Yeah, but we need independence somehow. Otherwise, if they were all equal, then everything will go on one side. Means if they are all equal, they are not independent. They are all equal. That means no. They are.
What do you mean by they are equal?
Uh,
X1 and X2 are there, like in our setting they are distinct, they corresponds to vertex 1 to n, right? So they all are distinct.
I mean, x1 and x2 are random variables, so they are the same functions.
Yes.
That will mean they are equal that way. If they're dependent, then
But they are not, no. I have defined my process for every vertex I have a random variable for which I assign this 0 or 1 based on my coin toss, and each coin for each vertex is distinct. Then I don't need anything. All it says is that okay, there is a partition with half and half. But look, Yeah, it should have, because it is at most 2 independence. So it is at most 0 independence, 1 independence is also part of this. But suppose I said the following line: there exists a partition of equal part and has at least m by 2 edges, then this also I can conclude with just 2 by independence. If I want to say there exists a partition in my graph, I want to say the following thing. Look, this is my process, and by which I want to conclude there exists a partition such that V1 is equal to V1 minus V2 is less than equal to 1. Means they are almost equal, right? Because n by 2 may not be an integer for all that you care, right? If I want to say this, there exists a partition so that this happens, and at least half the m by 2 edges are going across. Then what will you say? Can I conclude from here?
No, this doesn't guarantee that means any edge is in the.
Why?
It is just like.
I said there exists a partition with this property. Can I conclude from this random experiment? Look, my random experiment, oh, I randomly partition this into.
Yeah, some partition is there for sure, which one means equal size.
Yeah, but the same partition should also have this property, right? Because it's AND. Right? So I did one random partition. I said this random partition has this property. First, expected size is half, right? And
Then maybe okay.
you get my point, what I am saying, right? Look, I mean, I can try to make a very complex set of properties, right? And just use 2 random variables, like 2 by independence. And this function must give me one of those guys which also satisfy this property. So anything which you can deduce probabilistically, there is a function which satisfies this property, right? Because what is the whole objective of probabilistic method? Let's try to understand what is the whole object. There is a space where my objects are, and we say, look, this property holds with probability, non-zero probability. It means there is an element in my sample space which satisfies this property. This is the whole way, this is the whole goal of doing probabilistic method, right? So whatever objects you are interested in, you create a sample space on this, right? And you say that, look, probability that this holds is non-zero. It means those points where this property holds is non-zero. It means there is one point in my sample space where this happens. So such an object does exist. This is how we conclude from there. So anything, however complex creature you can create, right? Whatever complex creature you can create, and all you are using is limited, all you are using is this region, that if I look at any 2 column, they are uniform over this, then that set of function will satisfy this property.
Doesn't imply max bisections polynomial. In polynomial time, you construct this family.
How? What is the meaning of max bisection? No. All you can say that there exists a partition with at least m by 2 edges. That's all that it is. But max bisection, if I give you 3m by 4, how will you conclude this? But there could be a partition with 3m by 4 guys, right? But if I said you, is there a max bisection of size at least m by 4? Yes, always. Okay. Anyway. So now in our setting, what were we trying to understand? Okay, so this is all history, geography. Okay. So I would be interested in slightly different functions. Okay, let's write down and prove those properties first. Okay, so our functions will have universe is again 1 to n and to b. So it's basically those functions from universe, it takes 1 to b. Okay. So what is a property of a random function? Okay. So look, so now I define based on what is my ui is f inverse of I. So f is a random function. What is f? Is a random function. What I mean by random function? It assigns an element of u, an integer 1 to b with probability 1 over b, right? So this is what I mean. For all a in u, I in p, f of a is equal to I with probability 1 over b. And I define ui equal to fi. So ui is also a random variable? No, ui is a set. But this is a random variable. F inverse I is a set, but this is a random variable. Size of ui, the number of objects which has been assigned to element I. So what is the expected size of ui? This is my random function. This is my random experiment. And now I am asking you, what is an expected size of ui? Prove. I mean, this is a very simple question, right? I am not asking what is an expectation of ui.
Probability that j goes to I is 1 by b. Probability that j goes to I is 1 by b. For some j in u, probability that it goes to I under f is 1 by b. The expectation will be like that.
Yes. So basically what you do, as always we have been done, for all a in u, let's create an element xa, random variable xa, and what value xa takes, okay? So I have to, what is this? Xa is 1 if f of a is I 0 otherwise, because I just want to understand this, right? So why do I create? So clearly now I can say summation xa. Is this correct? Like for a fixed I, I am not interested in for all I, but let's fix one I, then this is what, because if f of 0 otherwise. Now we know how, but what is the probability that xa is 1? 1 by b. Right? So clearly because of this, expectation of ui is equal to n over b. Great. Okay. So what I would like to do, so if you recall from last, so this is correct. But suppose I would like to say that, oh, I am not interested in this only, I am interested in the following property. Not only ui is nib, but for all j, suppose I say, for all j in B, I am interested in this object. Okay. For all j in B, first of all, can we prove this? Ui is, for all j in B, uj is equal to n by b, for all. Is it possible to prove?
What you are trying to prove? So
For all j in B,
what you try to prove for all j in
for all j in B, cardinality of uj is equal to n of b. It's equal to its expectation.
you want a particular function. Yeah.
Huh? So what is the probability of that? Look, I am looking for a partition. Look, my interest is very simple. I have chosen a random function. Is there a random function if such that for all j in B, uj is equal to n over b? You have to be careful. You have to be very, very careful, because these are very dicey situation. Because imagine yourself, no? Yeah, if b does not divides n, then can you ever get equal to n by b? Okay. Okay. How hard or easy it is to prove?
There is a function.
Huh?
There is a function that is very easy.
But how much wise independence it will be? Let's see. Okay, and as you all point out, it's very easy. So for even if, right, it's very easy, right? What function is this? Well, you just take first n by b element into 1, next n by b element to second, and this function works. But suppose I not only had u, but I have the same function, but I also give you a set S. I give you a set S. Okay, I have some set S in my head. S is a subset of U. Okay, now what I am interested in is expectation of Ui intersection S. What is this? And suppose cardinality of S is Q. P Q. P P. What is this? It is this, P by B. Okay. Now, do you see where I am trying to go now? So if you remember our NPQ separating NPQ collection, what we needed to do? We needed to come up with the functions, right, with the following property, right? That if you recall that for every S, there is someone which is contained inside this, right? So what was this? What was this NPQ inclusion set family? Is basically, right? It was basically some x1, x2, xl equal to q, such that for all y subset of u mod u equal to p, there exists some xi in say our set delta such that xi is a subset of u, right? This is what we were interested in, right? And we constructed such a family delta. If you recall, we constructed a family delta of size, if you recall correctly, not too large, but of size, how much it was? If you recall, it was n choose q divided by p choose q and some say poly n factor, say some n to the power c, some fixed constant c. This is what we showed, but time we took was 3 power n. Right? I am not writing big O, but just to get you get to down the line what I am trying to achieve. This is what we did. Okay, like this we did last time. Now I want to do this. Okay, but what is my goal? This running time is too much for me. I cannot hope to have this. I would like to have running time which is like this, right? Which is not much more than this, right? Which is not more than this. So what I want to do, first of all, I want to take my universe and map them there. Okay, what I want to do? I want to take my universe and divide it into U1, U2, UB. Okay, it's a partition because this provides me a partition, right? And what I would like to do here, I would like to apply this guy. What I would like to apply is this construction, but I don't want to apply this construction for same P and same Q, otherwise I will not gain anything, I mean much, right. What I would also like that this S which is in your head is also divided here, roughly equal, right. It also divides roughly like 1 over B times its star. This is what I would like to achieve this, right. So what I would like to achieve, so expectation of Ui intersection S is P by B, and I would like to show that actually there is a function which, okay, this is trivial, this is very simple, that it will define n by b, I mean there are many such functions, that's fine, but it is also not too much away from like it is doesn't contain S too much, like it also divides S roughly equally in each part. And what is the meaning of roughly equally? I will define in a minute. What I mean by roughly equally, it is not too far away from its expectation, like from its mean it does not vary too much from means. Then what we will have to compute? If I want to show something does not vary too much from its means, then what do you compute? In probability theory, what you have to prove to show that something does not, like it does not vary too much from its mean. What is that? What do you compute? Variance. And you show that, right? This is exactly. But at the end you have computed variance. Okay, and then later you will apply some tail inequality like Chebyshov, Markov's to say, look, things are nice. That we do achieve this with non-zero probability, because at end of the day we have to go to the world of functions where we are playing all this game, right. We have to show that there is a function which satisfies all these properties, right. So suppose we were in this random world, now what I would like to achieve, so I give myself a little bit of leeway. I do not demand that each Ui is n by b, or they can also vary a little bit from their mean, and Si can also vary a little bit from its mean, okay, that is what. So now what I would like to do, what I would like to say, and for everybody, this is the whole point, for every j in B, they should not vary too much from its mean, that is important, okay. So what I would like to compute is this, but what I am actually primarily interested in to compute that probability for all I am actually interested in computing what is the probability that Ui of f, the function which we have taken, minus n over b, this, so this says that this minus this like neither too low not too much, I will quantify what it means, like from its mean, this is its mean, right, n by b, it is in this range, like it is not here or not here, this is what I would like to show, right, it is close to its mean, right. So this is why absolute value is upper bounded by, is say at least root n times b. I want to have an upper bound on this, that it deviates from its mean not too much. Similarly, I would like to show for the other guy, probability that Ui f intersection S minus what? P by B, right, P by B, this is what its mean is, right, like it is a P size object, it should minus P by B is greater than again root n times B. What is this? Suppose I prove this, something interesting, then how will I argue? If I prove this, that oh, this happens with some probability, say alpha and probability beta, what will this imply then?
That it is, okay, first of all, it means that it is close enough is at least that one minus that thing, so that will mean that such kind of.
So look, I have to prove for every I, right, I have to prove for every I, right. So what I have to show, there is a function which does not deviate from its mean in each part, as well as for S, it does not deviate from its mean in each part. Right? So what we have to show? Probability that it deviates in one of the part, if we are able to bound that for both, then we can take union bound. What do I want to achieve?
Even let's say before we had this S, you were saying we can always find a function which has the property that for all j which is equivalent, but we were taking the first and first.
I mean, there is a function. There is a function, right? That's all.
Even with this S, also you can do the same, right? You take the first.
But why the same function will achieve both? Look.
No. So
It should work for any S, no? Is that right?
No. For a fixed S itself.
if the S now you partition S.
But then why N is also partition?
That can always achieve it because okay, you partition S first, P by B, P by B, P by B. Map the first P by B elements to I. Okay. So S is already partitioned. There are some other things remaining. So if one gets mapped to the first part of S and other dummy things to come, like 10 you fill this N by B. And 2 gets mapped to the second part of S and the other N by S. You can always do that.
You can always do what?
I'm saying okay, you want a function where for look at any I in the number of elements of U that maps to I is N by B, and the number of elements of S that maps to I is P by B.
Agreed.
That's what you want. I'm saying just arbitrary partition S into B parts, P by B, P by B. Each.
Okay.
Now there are these parts. Now there are other elements of U. You can just arbitrarily keep adding these elements to the first part to make it N by B.
Good. Yes.
So there is always a function that is used.
Yes. But what happens there?
I mean, yeah. So what is more that we are trying to achieve here?
I'll tell you in a minute. Okay. Good. Let's try. There's such a function that exists, right? But how many such, like for each S, I will have to create one function, right? How many such functions are there? How many such functions will you create? For each S, you will create a function, right? Which is like n choose q. N choose q. Because no, S is of size p. Sorry, so n choose p. Are we doing something wrong? Which is bigger? P. Fine. So we'll create n choose p.
No. Okay, yeah.
We'll create n choose p such functions. You are right. Such n choose p functions exist. You see what I'm saying?
What is the corresponding?
Look now. So how many such functions will be there? For each S, you can create one such function.
So there will be P,
N choose p. So yes, when we have a leeway to create n choose p function, this is perfectly fine. But imagine if I tell you that no, you cannot create n choose p function, and if I tell you that all you can create is n square function, now what will you do? Or I say you n to the power 100 such functions, which should be able to do it for every S, right? So we are analyzing for a particular S for sure, right? I have taken a random function and we say, okay, what is the probability that it is good for this particular S? Because S is an arbitrary object. If in this computation, somehow I use some limited independence, and what I mean by limited independence, here I have used unlimited independence. What I mean by unlimited independence, for every element we have a random variable, right? Every element I have a random variable, which takes value from 1 to b, with probability 1 over b, right? So for every element you have a random variable, right? And when you try to prove such statements about objects, if it is too many things which needs to go together, then the size of this object will be too much, right? So suppose if all I am interested is that, look, I want to achieve this property that it partitions every S properly, whatever properly means this, okay, but I don't have too many functions, right? I cannot afford, Rohani, I cannot afford to have more functions than this, right? right? That is also my goal. I cannot afford to have more functions than this because I am trying to obtain a family which is of roughly of this size, right? So if I start itself via partitioning, what is my goal? I explained to my goal. My goal is that objects get partitioned into small pieces such that in each piece I want to apply my bad running time construction. Am I right? That is my whole goal.
So where is the unlimited independence that is used here?
In where?
Here. Are we using any? Where are
We have not yet used. We have not yet used. But how are you constructing these u's? Look, this is my function, right? This is my function. How did you construct this function? For every variable, you had a b-sized coin toss.
Yeah, so I had B different points.
No, you had n different coins. I already used independence. How did I construct my f? By n different coins. How did I construct my f? The f is my random object, right? How did I construct that f?
But is that the meaning of independence? For example, even in max cut, we
Yes.
had n different coins.
Yes.
But it was two-ways independence because
No, that we later deduced that we don't need more than that. But in the beginning when we were creating a partition, look, for each x I had n different random variables.
So are you saying that we can do this max cut and the partition with only 2 coins?
No.
So these are different things, right? The number of coins that you use and the
Yes, but what did I use? I did not tell you how I constructed these functions to you, right? But at this point of time, all you know is this is how you construct your function. For each guy, you take a b-size coin toss and do this, which is nothing but how much it will be. How many such functions will be? Think about it. B power n. It will be b power n, which is a lot, right? So similarly, when you had, there were 2 power n such object, right? So when I just directly try to translate these functions into my deterministic object, right? What I can do, I can go over all sample space from where I am picking these functions, right? Because then only I can be sure that there is one function which satisfies this property. But then if I go over all its domain, it's already b power n, which is huge. I cannot afford to go. Similarly, in max cut, I already had gone over 2 power n. So now I am saying that look, this is a domain of these functions. Now I am trying to analyze this and say, oh, no. I don't care that you use n coins which are independent from each other in a large way, but all I care that 2 of them, 3 could be dependent. You could be using the same coin for, coin is not a right way to understand this. This is not a right. All I am trying to tell you that look, currently experiment is happening in different rooms and n different rooms and people are just producing and giving out. Now I am telling that look, it's okay in the same room 4 people or 5 people are doing experiment till 2 people don't care about each other, right? And these are 2 different things. So when I say that okay, let's use the full power of these random variables, like use it like 3 bytes, 10 bytes, 100 bytes, I really have created my functions, each element, each constituent of this function independently. So basically my whole world is b power n size function. What is my whole world? I am working over b power n size function. But if in the properties which I want to deduce, I do not use the full power of this b power n function, then I can find a small set of functions which does my job, right? So currently our world is b power n size, right? And we are trying to deduce the properties. But if I can prove that all I needed this property is that for every set S, right? What I want for every set S, it does not deviate too much from its expectation. Up until now, if you notice, Ronnie, up until now, computation of this, what Bayes independence we use? Nothing. Computation of this, what Bayes independence we use? Nothing. Right? So up until now, this is in control. Oh, I don't need too much. I don't need all of them to be completely free. Right? Up until now, we are able to conclude this much. But now, the bigger conclusion I need to draw. Right? If in doing this, I need huge unlimited objects, then I cannot say anything. But if I can control even this with small number of independence, then we can say, okay, it means I don't have to go through this b power n number of functions, but a small number of functions. That a small will be quantified once we prove this lemma, and it's good enough for us to look into those functions.
And the reason you're doing this variance process is it because with the exact thing you can't really prove a constant wise independence?
Yes, no, not constant probability,
No.
not constant.
Wise or whatever wise independence you're
Yes, that's one reason, as well as like how do I apply Taylor inequality? Look, there are some computational difficulty, and there is technical difficulty, right? So what I mean to say this, look, if you demand exactly equal, you can prove that you need roughly n choose b. So I need to allow certain amount of freedom.
So it's because you can't.
That's one thing you cannot even prove this statement. Like, I mean, what I mean, you cannot prove such set of functions do not exist. If I demand that the way you constructed your family, that both should be exactly equal, then we can come up with an example where you need roughly like n choose b. Okay, so if for that property you need that much, right? How can a probability be helpful to you, right? So that is why you allow certain amount of freedom. So this is the freedom. This is the freedom which I am allowing, right? Now, how much you can absorb in your algorithm freedom, that you have to quantify based on the what running time you are trying to achieve. That's the first thing to do, right? I cannot put b equal to n here, for example, right? Because look, I would like ideally to be as small a world as possible. Okay, so now I want to compute this, right? How do I compute this? How do I compute this? Like, look, this is a very simple thing. It's not, I'm not saying anything big. Look, this is a simple probability computation. Look, if you understand this, then the construction is really obvious. And it will be obvious for almost everything. No, but first what we need to show. I want to argue, right, first of all, that this function satisfies this property, right, for every I, for every j. For what I want, for every j, for all j, this happens. I want to show what is my whole goal, right? So if I want to say probability, okay, so I call a function f good, a function h from u to b is good for S subset of u if these two properties are satisfied. Okay, ui minus f minus n over b is less than equal to root n times b, and this is what I want to prove. A function h is good for a particular set if these two properties are satisfied. To be
H from U to B.
Yeah, it's b, not n. Is good for a set S. What is the probability that f is good? Okay, so how do I compute it? I'll say, oh, what is the probability that f is bad? Probability that f is bad is upper bounded by sum over this and sum over this, right, by union bound, right? Probability that f is bad, it means either this fails or this fails. Oh, if one fails, it fails because it fails for one of them. Oh, if b fails because it fails for one of them. So basically what you have to do for this, you sum over this and this. So what is this? It is basically alpha plus beta times b. So if this is strictly less than 1, then we are good. It means probability that it succeeds is with non-zero probability. I am not interested in constant probability, nothing. All I am interested in a non-zero probability. That's it. It means my function will exist. Okay. So this is my whole goal. Now, how do we show this? And then we will end the class for today. Okay. So did you understand why I said that this is good enough? Because if I prove this, then all I need is alpha plus beta by b should be less than 1. This is it. Okay. What is this? What is the variance of f? What is the variance of UIF? Okay. Okay. So you understand what I am trying to say here, right? So let's just forget about this. Let's just concentrate on this because then we are done. All we have to show here, let's write down here, alpha plus beta times b should be less than or equal to 1. That's all that we need to show. Okay. So let's go back to UI. I should have written, no need of writing f here, okay? I don't know why I'm writing f here, it's okay, fine. Because you will see when f comes, when it comes, not now. Because f is a fixed object anyway for now, for fixed function, fixed random function.
Is this UI and that UI same?
Which UI?
That
Of course they are same. They are random variable. Okay, I think I wrote something. Yeah, you're right. I should be writing, here we use, see this is what happens. No, you're right, you should be writing underscore. Same, they're same, they're exactly the same, they're nothing different. So now how do you show this, right? So there are ways to show all these things, right? So I mean, if I want to show this is upper bound, I have to apply some tail inequality, right? So either you apply Markov, you apply this, based on what you apply, right, that much independence you need, right? And you know that as the moment, what is if you recall correctly, what is Markov inequality? Probability that x is greater than a is less than or equal to, right? And what is, I mean, I'm writing it not completely correctly, otherwise you have to put them in a, for all x being a non-negative random variable, blah 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 blah. But you know that you can prove much better upper bound or lower, upper bound on the probability if you consider larger and larger moments, right? Larger and larger moments, and by moments what you mean? X power k. Why? Because it approximates the object much more closely, right? So you can also show Ex power k or something, but what does Chebyshев says? It is only for 2. Right. So this is where you will have to see, okay, to upper bound this probability, what kind of dependence is good enough for me, right? Because if they are not less than or equal to 1, then what am I doing, right? So this is where you need certain amount of freedom to prove some things, not before that, okay? So what did Chebyshев says? Basically Chebyshев says that probability x minus expectation of x, which is what it is, some number t,
variance of x by t square.
okay, and what is the variance of x square?
Variance of x, that is expression of x.
Variance of x this, okay, and what is the variance of xi? I going from 1 to say M is nothing but is variance summation, what am I doing, summation variance of Xi, and you have to subtract, I think, covariance, I think some
Variance of Xi, Xj or
something like that, okay, but fine, I don't think we need that, okay, I don't think we'll need this, okay, but imagine that covariance is nothing but, and there is some covariance terms, okay, some covariance term over some Xi, Xj, this is what it is, okay, it is not important for us, why, because what is the definition of covariance of Xy? Is nothing but expectation of Xy. So if X and Y are independent random variable, then what happens? So if X and Y are independent random variable, then covariance of X comma Y is 0, because they are, what is a covariance? They are correlation to each other, I mean if you think, so this is equal to 0. So basically in our setting we will always, this will be 0, okay. Now let us go back. What is cardinality of Ui? I wrote what this is, right? What? So I am going to compute variance of, right? So what is this? So if look at this formula, all I need to compute is the variance of Ui, right? So if I am interested in computing variance of Ui, which is same as variance of what? Summation over Xa. Now suppose I assume that Xa's are pairwise independence, right? Or all I care about that, I mean any two guys here, if you look at the column, two columns, what values they take, they are independent. That is all that I care. That will immediately imply that any two guys Xa and Xb are independent, because they are dependent on F. So if F takes at two places two different values with equal probability, like one, if I look at those two columns, if they are same, then I can say that Xa's are also, these random variables, indicator random variables are also pairwise independence, okay. So think of this way, how? So as Rohani says, how did we construct F? Think of F construction as nothing but F is constructed from Z1, Z2, Zn being a random variable, there are n random variable, and each one of take the values 1 to b with probability 1 over b. These are my n random, independent random variable. So if these are pairwise independent, then you can show that Xa and Xb are also pairwise independence. What did I say? If Zi's are independent, pairwise independence, then so is Xa and Xb. Okay. Now these are like really high school computation if you think about it. But now this is variance of summation Xa, but what will happen? Covariance term will go away, right? Covariance term will go away because they are pairwise, I am assuming that they are pairwise independence. For now let us just assume that Xa's are pairwise independence. So this covariance term will go away, and what is this variance of summation Xa? It will become summation of variance of Xa A in universe. But what is variance of Xa? Now variance of Xa, we had a formula here, expectation of x square minus expectation of x the whole square. What is this? So expectation of Xa square minus expectation of Xa whole square. What is expectation of Xa?
That is 1 by b.
1 by b, right? So this is 1 over b square. And what is expectation of Xa whole square? Xa square takes value 1 or 0. It takes value 1 if and only if Xa is 1. That happens with probability 1 over b. So this is 1 over b. Xa square takes only two values, right? 1 or 0. 0 it takes with probability 1 minus 1 by b. So that forget 0 anyway. 1 into, it takes 1 if and only if Fa is 1. So we computed this. Okay, are we done now? Look, right. So for one guy we computed summation, okay, summation. But what is this? This is equal to n times 1 over b minus 1 over b square. This is n times this, which is less than equal to n for all that I care. This is true. N by b minus this. Okay, I computed. Okay. So we have computed this. Now what is this? So variance of ui minus nb greater than equal to root n by b. If I apply this, what is this?
It is n divided by
1 over b square.
1 over b square.
So this we proved to be 1 over b square. Right? Just apply this. Right? Is less than equal to n. So variance of x is n.
So that 2, okay. T is that thing rooted into vi.
Yes.
B square.
Yeah, it is cleverly chosen. Don't worry. Okay. Okay. And actually, by the same kind of computation, you can show 1 over b square. So what is alpha plus beta?
2 by b square and that multiplied with b is 1 by b. So that is less than 1.
So no,
No, just 2 by b.
it's 2 by b.
2 by b, right?
It's 2 by b, right? But if I choose b greater than equal to b strictly greater than 2, then I'm happy, right? So I'll choose b greater than equal to 2. So b in our setting will be greater than equal to 3. Okay. So what we have shown that if I start with a random function, and what did I use? What did I use throughout? All we did is that only one thing which we have used in the whole computation is that x's are in pairwise independence. We never use anything more, right? To get rid of this covariance factor, we said that okay, these xa's for this particular guys are what? Pairwise independence, and here we use, right? We said this is 0, and I said that covariance of this, right? And if xy independent individual, this is 0. So when I write variance of summation ai is variance of summation xa. But what is variance of summation xa? It will be some variation of xi and minus some covariance term, like covariance of some xi xj, whatever this is from. So it will be some xa, xai, xa, xb. I want this term to be 0. So what I just assume that they are pairwise independent. Otherwise computing this becomes a mess. Okay? Computing that will become mess. So I just assume. So all I assume that here these random variables are pairwise independent, right? These random, indicator random. That is all that I used. Okay. Now you try to show yourself now that suppose, and how did I construct it? Right. So in language of x, in language of Zi, what this will be? For all a in I, u, xa is 1 if Za is equal to I. This is if I use this language, not F language, if I use the language of Z1 to Zn, what is this? I am going to create this function. How? Z1 to I have n random variable over, so Zi is a random variable from u to b. Zi is a random variable from u to b. No, what am I writing? It's not from u to b. Zi is a random variable from I to b. It's singleton. For every index, every element in universe, I have a random variable. So Zi is from I to b. I have constructed f by concatenation of these functions. Right? So I can think of f as nothing but which depends on this each individual random variable. Now I can, if I think of this as individual random variable, then, and I say that okay, this Zi's are pairwise independence, then you can show that this xa and xb's are pairwise independence, right? What does it mean to show that? Look, okay. So what we have to show that they are pairwise random variable in it. So for all, okay, so for all I comma j in U, or let's say for all a comma b in U, I comma j in B, right, probability that xa equal to I and xj equal to B, what am I writing?
Aggregate A and C, B you have overused.
Equal to G.
B you have overused.
Oh,
A, C, or C.
okay, let's call it
Use you.
CD. No, C also we have used. Say EF. I mean,
F you overused.
X y.
little x, little y. Okay? Fine? Is equal to 1 over b square. This is what you want to show. This is what it is. Right? This is all that you have to show. By pairwise independence, this is exactly what it means. Look at the two column, right? What is those two columns? Is a column of x and y, right? It is a column of, so look at my matrix view. Here is a column of x and here is a column of y, right? And what is I comma j? Is any value between 1 over, like, is between b, and all I am saying that you can get any value with faulty exactly 1 over b square. So it is uniform over this domain. This is exactly what it is, right? Okay, so this is equal to, so this is what need to show. So what is the probability that xx equal to I? Well, this is same as x is equal to I if and only if za equal to I, zx equal to I. So probability zx equal to I if and only if it is zy equal to z. And by our definition, z a pairwise independence. So that is it. So like any guy which, so what did lesson number 2? If I have defined a random variable which is a function of some other random variable, then whatever the independence property they have, it inherits. Why? Because you can always write this in terms of other. Okay? I given you a formal proof that why? Because this is what you define. Xa equal to 1 if this, 0 otherwise. So this is equal to 1 if and only if za equal to I.
I and J should be from.
No, this is wrong. See, I j is element of 0 comma 1. It has not be. This is wrong. I comma j is element of 0 comma 1 because this is what it takes. They are random variable. Right? So then you shouldn't be writing 1, right? So xx equal to I if zx, oh my god,
No. Ij is in 0, 1, okay, fine.
because that is what xx takes, right? And then we don't have to show 1 over b square, we have to show 1 over 4. That is what we have to show. Okay? What, this is what you have to show. So
Xx equal to 1 if za equal to I.
because
No,
that
this I and, okay, that's fine. Now I can be
No, now
anything
we
from
have to
1
sum
to b,
over
right?
I.
you have to sum over I.
No, I can be anything from 1 to b, right?
Huh?
I can be anything from
1
1
by
to
b
No.
squared.
Look at
sum
x,
over
how you have
b.
defined.
Fixed right for that case.
Look at how xa is defined. Like given zi, I defined my xa. So once I fixed one zi, I have defined this. Now you have to sum over each, sum over all I comma j, which I am not in mood to do, but you will get it. This is like a high school computation. Okay? Yes.
Even if I keep the covariance term, is it only the negative terms or will there be some plus terms later on?
I don't remember what the definition
Because
of.
if it's only the negative terms, why do we need the pairwise?
I think there is some, it's minus plus depending on,
Something if it's exactly this, if it's summation over variance xi minus some terms.
No. So you're claiming that covariance is always a positive quantity. Then you could have used variance. That is what you wanted to do.
Yeah, I'm saying there.
Upper bounded by
Whatever.
variance.
Yeah.
but covariance can be negative.
-1.
Covariance can be negative. I think it's only minus, right? Yeah, you have a variance, you sum, and then you subtract each of these guys. Yes, this is fine. It only will be minus.
Suppose it was just positive, so she was saying that you could have used upper bound as
Yeah,
variance.
you don't
Yes.
have to-
Then you don't need it.
So basically, we need only independence when it is covariance is absolutely negative. So we can show that there are random variables when covariance is positive, and then we are done.
Yes.
Then you want to construct a family with covariance such and such.
No, I want to have a procedure where the random variables have covariance.
Yeah.
Yes, you could create that.